given a function f of x is equal to the sine of x with a equaling pi over 6, we're going to approximate f as indicated, use Taylor's inequality to estimate the accuracy over a given interval, and graph the remainder function r sub n of x. Our work now builds on what we did in part A of this section, and so if you haven't seen that video, please watch it now. The instructions we are given are going to be to find the fourth degree Taylor polynomial, so n equals 4, and then the interval that we're given is from 0 to pi over 3 for the value of x. In our previous work, we found the first three derivatives of f, and we found that f evaluated at pi over 6, and the subsequent derivatives f prime, f double prime, and triple prime, were 1/2 square root of 3 over 2, negative 1/2, and negative square root of 3 over 2. Here we're asked for the fourth degree Taylor polynomial, n equals 4, and so we need the fourth derivative. And so when n equals 4, we have the fourth derivative of x is equal to the sine of x, and the fourth derivative evaluated pi over 6 is equal to 1/2. Again, from our previous work, we already had some terms of a Taylor polynomial. Here I'll write down that t sub 4 of x is equal to, and then I'll bring in our previous work. And we had gotten as far as 1/2 plus square root of 3 over 2 times the quantity of x minus pi over 6 minus 1/4 times the quantity of x minus pi over 6 cubed minus the square root of 3 over 12 times x minus pi over 3 cubed. I said cubed a moment ago, I meant negative 1/4 times x minus pi over 6, the quantity squared. That was t sub 3. We need t sub 4. And so we need to add 1/2 divided by 4 factorial x minus pi over 6, the quantity to the fourth power. That gives us our fourth degree Taylor polynomial. And that is the answer to part A. Well, really I should simplify this. 2 times 4 factorial is going to give us 48. For part B, we are to use Taylor's inequality. Let's recall, if we have a number m that is bigger than or equal to the n plus first derivative of x for an interval x minus a in absolute value that's less than d, then r sub n of x in absolute value is less than or equal to m, that m, over n plus 1 factorial times the absolute value of x minus a to the n plus 1. Let's put this in the context of what we're working with. What we're working with is that n is equal to 4, a is equal to pi over 6, and the interval that we were given was x goes from 0 to pi over 3. What we want to do is a couple of things. Number one, I need to determine what m is. For that, I need the n plus first derivative of f. Since n is 4, that means we need the fifth derivative of f. As we saw a moment ago, the fourth derivative of f is equal to the sine of x. Therefore, the fifth derivative, right, the n plus first derivative, is equal to the cosine of x. Since we know the derivative, well, the fifth derivative, and the interval, which is from 0 to 3, we can determine m. On the interval x going from 0 to pi over 3, the fifth derivative of x is less than or equal to 1. We have a maximum value for the cosine function when x is equal to 1. Therefore, we're going to use 1 as our m. Now, as far as the absolute value of x minus a, we consider that x minus a in absolute value is to be less than or equal to d. That's from Taylor's inequality statement. We're going to start here with the fact that x was given to be between 0 and pi over 3. That's the interval we were working with. Now, comparing this inequality here, 0 less than or equal to x, which is less than or equal to pi over 3, comparing that with x minus a is less than or equal to d, that x minus a is an absolute value, the difference between this middle value in the compound inequality x and what's inside the absolute value is that the absolute value is x minus a. A is pi over 6. And so what we're going to do is we are going to subtract pi over 6 from all three parts of this inequality. So x minus pi over 6 will then be between pi over 6, negative pi over 6 and pi over 6. Now, if we think about solving an absolute value inequality of the type absolute value of x is less than or equal to b, one way to solve that is to write a compound inequality, negative b is less than or equal to x, which is then less than or equal to b. We're going to actually take these steps in reverse. If x is between negative b and b, then the absolute value of x is less than or equal to b. Here I have x minus pi over 6, which is between negative pi over 6 and pi over 6. Therefore, we can say that the absolute value of x minus pi over 6 is less than or equal to pi over 6. I'd like to point out that the pi over 6 inside of the absolute value is because a was pi over 6. The pi over 6 on the right-hand side of the inequality is a coincidence that it matches a, because it was the result of subtracting from all three parts of this original inequality. Bottom line here, I now have a number that I can put in place of x minus a in Taylor's inequality. Putting this together, we can say that r sub n of x in absolute value is less than or equal to 1, that was our m, over 5 factorial, I don't need to write it as r sub n of x, it should be r sub 4 of x. We have a specific n. So the absolute value of r sub 4 of x is less than or equal to 1 over 5 factorial times pi over 6. That's coming from the right-hand side of our inequality to the 5th power, because it's supposed to be to the n plus 1st power. Using a calculator approximation, we see that the absolute value of r sub 4 of x is less than or equal to 0.000328. And that takes care of part B. Part C was a graph, and so let's look at what we have. For the graph, we are considering that the absolute value of r sub 4 of x is equal to the absolute value of f of x minus t sub 4 of x. Now f of x was given to be the sine of x, and t sub 4 of x is from above, right? Part A. So I've graphed here the absolute value of the sine of x minus the 4th degree Taylor polynomial. You can't see it here, but there were a lot of terms I typed in. And this curve that we have here in purple is the remainder function here. The original interval that we were given is that x was to go from 0 to pi over 3. So I have a vertical line here at 0 and another vertical line here at pi over 3. And what we can see here is that the value of r sub 4 of x on this interval is never bigger than 0.0003. And in fact, for most of it, it's smaller. But the Taylor's inequality is, it gives us the maximum error. And as we can see here, we had computed 0.000328. So 0.000328-ish, sure, I buy that. Actually, come to think of it, the purple curve intersects the blue vertical line at a value that's less than 0.0003. Bringing to mind that it's Taylor's inequality, we were told that the error would not be more than 0.000328. Turns out the maximum error on this interval is actually a little less than that,